Lesson 43, the chi-squared test for independence. One specific application of the chi-squared goodness of fit test involves testing the assumption that two events are independent of one another. That is, to determine if the categories of two qualitative variables have no effect on each other. This adaptation of the chi-squared goodness of fit test is referred to as the chi-squared test for independence. The expected frequencies used in the chi-squared test for independence are generated under the assumption that the two events are independent of one another. Since two events, E and F, are considered to be independent when the probability of E given F equals the probability of E, the predicted proportions of each category in this test are the probabilities of the corresponding categories of each event E. Now this chart displays the steps we follow when conducting a chi-squared test for independence, starting with stating the hypotheses. The stated hypotheses, HO and H1, in the chi-squared test for independence are always expressed in the same manner. HO is always that the events are independent, and H1 is always that the events are not independent. Now after the hypotheses have been stated, we then could identify the alpha or level of significance of the test. Unless there exists a compelling reason to do so otherwise, hypothesis testing procedures are conducted using the customary 5% level of significance, or alpha equals 0.05. Next, we can use the chi-squared test command on the TI84 calculator to calculate the p-value required to reach the decision in the hypothesis test. But first, we need to enter the observed frequencies into the calculator. The observed frequencies, or sample data, can be organized in a contingency table. A contingency table is a table where the categories of one variable are arranged across the rows, and the categories of the other variable are arranged along the columns. Here's an illustration of a contingency table. The first qualitative variable has R categories. So these are displayed across the R rows of the table. The second qualitative variable has C categories, and each of the C categories are displayed along the columns. Data organized in this manner can be entered into the TI84 calculator as an R by C matrix, where R represents the number of rows and C represents the number of columns. After the observed frequencies are entered into an R by C matrix, the chi-squared test command on the TI84 calculator will calculate the desired p-value for the chi-squared test for independence. Now to use the TI84 calculator to enter the observed frequencies into an R by C matrix, we press second, matrix, and then arrow over to edit. Then we arrow the cursor next to the matrix we want to enter the observed frequencies in. The matrices are labeled A, B, C, and so on. Press enter. Then we enter in the number of rows in the contingency table and the number of columns in the contingency table. Then we enter the observed frequencies in the contingency table, row by row, all across the first row, all the way to across the last row. Now to get to the chi-squared test command, we press stat, arrow over to tests, and then arrow up to place the cursor next to chi-squared test. Press enter to select, and then next to the observed, we enter the matrix where we entered the observed frequencies. We can get there by going second, matrix, and then placing the cursor next to the matrix we entered the observed frequencies in, and select enter. Expected is where we tell the calculator which matrix we want it to store the calculations of the expected frequencies. Arrow down to calculate and press enter. And the results of the chi-squared test calculations are displayed, including the p-value, which we use to reach our decision by comparing it to alpha, the level of significance. Now the formula that's programmed into the TI84 calculator's chi-squared test command is given here. The test statistic for this hypothesis testing procedure adapts the chi-squared goodness of fit test statistic to accommodate the categories of two qualitative variables, where the expected frequencies are determined under the assumption of independence. Now, the calculation of this formula and the calculation of the expected frequencies under the assumption of independence is all done in the TI84 calculator. In order for the chi-squared test for independence to be applied, the independent random sample must be sufficiently large. This can be accomplished by ensuring that the sample size is large enough so that all, or nearly all, of the expected frequencies are 5 or more. Also, none of the expected frequencies should equal 0, because in this case, the chi-squared test statistic would be undefined. Now, the calculated p-value is used to reach the decision regarding the validity of HO. Small p-values provide sample evidence contradicting HO. That's why when the p-value is less than or equal to alpha, we reject HO. And large p-values provide sample evidence consistent with HO. That's why when the p-value is greater than alpha, we do not reject HO. So now, based on this decision of whether we reject HO or not reject HO, we can interpret the result to state our conclusion. When HO is not rejected, the conclusion is that the events are independent. This indicates that there is no relationship or association between these qualitative variables. Thus, the variables do not affect each other. When HO is rejected, the conclusion is that the events are not independent. This indicates that there is a relationship or association between these qualitative variables. Thus, the variables do affect each other. So now that we've covered the steps required in a chi-squared test for independence, we can apply what we've learned in this lesson in the following examples.